What we're going to be looking at here is that an object will not tip as long as its normal force is located under its base of support. We are now talking about objects that have a length of its bottom that is going to be in contact with another surface or with the ground. We've looked at some tipping problems before where we had a point of contact between our object and a surface, and we said that tipping would occur if that normal force, if that contact force dropped to 0. And we're still going to look at cases where we have only a point in contact, but when we have two surfaces in contact, our thought process is a little bit different. When two surfaces are in contact, we can treat the force between them now as some distributed load because there's going to be a little bit of force distributed along the entire length or surface of contact. But as we know from working with distributed loads in the previous section, a distributed load can be simplified to a point load at a specific location, and externally that is going to be equivalent to considering that entire distributed load. So really what we're talking about here is that simplified point load that we're calling the normal force and its location between the two surfaces that are in contact. So for two surfaces in contact, when they are on the verge of tipping, or one is on the verge of tipping around a pivot point, what we're looking for is that normal force or that simplified point load normal force between the surfaces. If it is directly at the edge of this base of support, that means that our object is just on the verge of tipping. So the normal force itself does not drop to 0 when two surfaces are in contact, but the location of the simplified normal force or the equivalent normal force is right under a corner or an edge of that base of support. And still, if it's a point in contact with a surface, then tipping or being on the verge of tipping is when the normal force itself is just going to drop to 0. That is considering something on the verge of tipping. Now we can also test under certain circumstances, would an object be tipping or would we maintain static equilibrium? So here we can find, assuming we're in static equilibrium, get our equilibrium equations out, we can draw our normal force and we can draw it some distance from a corner of our object. And what we're looking for is, assuming static equilibrium, where would the equivalent load, that equivalent normal force, be for static equilibrium to occur? If that normal force is located under the base of support or under the edges of where those two surfaces are in contact, then static equilibrium is maintained. We are able to not be tipping under those circumstances. However, if we find that the location of that normal force is off the base of support, so to off the extreme edges of where the surfaces are in contact, if the normal force would have to be located outside there to maintain static equilibrium, that means our assumption of static equilibrium is incorrect and the object would be actively tipping. If the object is tipping, it is now a dynamics problem and it's outside the scope of what we're looking at. So how do we go about solving problems where we have the possibility of slipping and tipping?